Hello, my name is Alexander. Today I'm going to give you a quick overview of some work myself and my colleagues did over the past year to provide a CUDA backend to Intel's open source DPC++ SYCL implementation. To give you a quick overview of SYCL, in case you're not familiar with it, it's a single source C++ heterogeneous programming model managed and created by the Kronos group. It allows you to write your device kernels in C++ in line with the rest of your program and select devices for them to be scheduled with and dispatched to at runtime. These kernels can also be run as normal C++ at runtime for debugging, or if you aren't on a heterogeneous system to dispatch them to. I'm going to discuss the whats, but not the hows, of the major tasks of implementing this new CUDA backend for DPC++. This includes the Clang driver modifications we had to make, the PI library used by Intel SYCL runtime for device communication, how we interact with it, and we'll briefly mention performance of the backend at the end too. Note that this isn't everything required in a SYCL implementation or in the creation of the CUDA backend, but it covers the major parts of implementing a new backend for DPC++. The SYCL compilation model requires multiple compilations of the initial source file to isolate device kernels and compile them to different targets, be that SPEAR, SPEAR-V, or NVPTX. We had to add a SYCL PTX compilation path to the driver, which would produce PTX from the LLVM backend, then pass it through NVIDIA tools until we get a fat bin we could link and embed in the final application. The host compilation path is a normal C++ compilation path until the final stage, at which point we embed all device kernels in the final binary. The SYCL runtime connects to devices through the PI library, which in turn uses backend libraries for different platforms. The PI library handles each backend library as a separate platform instance with individual devices attached to them. Scheduling is handled by the SYCL runtime, but all device interactions and dispatch are done within the PI library and its backend components. Backends are loaded at runtime only as required. To do so, the PI library provides a function dispatch table that a backend must fulfill and connect to when loading. The first PI backend implemented was for OpenCL, and the functions in the dispatch table reflect this. We implemented about 95 functions for the dispatch table in the CUDA backend. Some were as simple as one-line CUDA calls to replicate the SYCL behavior required, but others were much more complicated and required notable framework within the backend. The PI library also requires a collection of opaque containers that can be passed in and out of a backend library. Thankfully, the containers should never pass between backends, so each can implement the contents however they need. This was very important for certain points during the CUDA implementation where more details need to be carried inside these objects than in the OpenCL counterparts. For performance and ease, we implemented all the SYCL built-ins we required for the CUDA backend in libclc and linked against that during compilation. In the end, our performance was pretty good, competing very well in benchmarks with OpenCL backend and the native CUDA benchmarks. There's still further space for optimization work though, and we expect to see further speed up in the future. If you're interested, you can get the repo and build from the source at github.com/intel/LLVM. We also provide a getting started guide and some code examples specifically for the CUDA backend. Thank you very much for listening. I hope you found this interesting. If you have any questions, you can reach me at alexander@codeplay.com. Stay safe and have a wonderful day.